Hello, this is an introduction to the latest version of the agent add-on for Grasshopper. So let's get started. The first thing you're going to need is a construct agent component. This is what's going to tell your agents what settings they have, things like lifespan, a mass, a maximum speed, a maximum force, vision angle, and a vision radius, among other things. This component gets fed into the system component, which is going to take in a list of agent settings. In this case, we just have one. If you wanted multiple different agent settings for different agents, you could feed in a list into any one of these inputs. The other thing the system component needs is an emitter. So we're going to use a simple point emitter for now. That just takes in a point. If it's continuous flow, at every time step, it's going to emit an agent. So we should see it emitting an agent at every time step, and we're going to feed the system into the engine component. This is what's actually going to run our simulation. Now the next thing we actually need to do is to deconstruct the system so that we can get to see its list of agents as well as the agent collection, which I'll explain in a bit. And then lastly, you actually need to deconstruct the agent in order to get to its position, which you're going to be able to see its point. So now I need to let's keep this set to true. So we're going to say reset, meaning don't run the simulation. We're also going to add a timer object. I'm going to set the interval to something low, and I actually have to hook it up to both the engine and the system. So this is kind of the setup you're going to need. And now, when I run the simulation, you'll see that agents are emitted at every time step. They're given a random initial velocity. You can control their initial velocity with this component if you wanted to. And you can start adding forces. So how do you start adding forces? So here we have, these are called Boyd forces. These were created by Reynolds back in the 80s. So let's see what a cohese force does to our system. So in this case, if I feed in, so this is for each agent, if I feed in the list of agents and the agent collection, every agent is going to see every other agent in the system, no matter how far away they are. But if this is not what I want, and I actually want them only to react to agents that are nearby, I can use this neighbors component. So this is a get neighbors in radius. And so that's why this thing outputs this thing I call agent collection, which is essentially a spatial data structure that allows for fast lookup of neighbors. So let's feed our agent to here and our agent collection in here. Now you can see our vision radius is set to 5 and the angle is set to 360, so it sees all around it. Anything that's 5, you have to find 5 units away. So now let's feed that in here. We shouldn't really see any difference because they're already so close to each other. So let's reset it, and let's add maybe a second point emitter over here. And now they're being emitted from both these places, and they're still seeing each other, but let's see if we get them farther enough away where these guys, so now you can see these guys are not able to see these other guys over there because they're too far away. Whereas if I had removed that neighbors component, everyone's able to see each other. So let's keep with the neighbors component. We can reset. See our two different, actually in the same system, but they can't see each other right now. So let's add one more force here. I'm going to add in a separate force. So say if someone gets too close, in this case, they're kind of all bunched up here. If I want them to be a little more spread out, then I'll use this component. Now, one trick we can use to speed up the computation, because there's a lot of computation going on here. Each agent might have to look at every other agent in the system. So let's try to reduce that by nesting these neighbors components. So as long as my vision radius, so I'll set a vision radius of 5, and I'll say that I want my neighbors to separate if they are 1/3 of that vision radius away. So things that are 1/3 of the maximum vision radius, they'll separate from. So let's feed in again our agent here. So now you can see they're separating, but still generally trying to stay close. And as I raise this, you'll see they get tighter. 1/7 the way they're reacting, whereas 5 units away now they're reacting. So usually I think 1/3 is a good happy medium between these two things. So that's the basic setup. You can do some cooler things like add in a position history. So let's say I set this to 5. Now it'll save the last 5 states, positions that my agent was in, and if I run an interpolation curve between these things, so I'll take this as a position history here, I'll shoot it through there, you can see I get these trails of the agent's positions. The other thing that's nice to do is be able to display or kind of preview what force was applied. So in this case, if we look at the cohese force, we could see all of these guys are generally trying to steer towards each other, whereas the separate force, they are separating from each other. So you can see the difference. So it's a really nice way to be able to debug your system. So I'll turn this off. And there you go. Hopefully that gives you a good idea of where to get started. Feel free to play around and just try out different components, different settings. Each one of them will have a different effect. And I think it really just takes a lot of tweaking and tuning to get a sense of what each one of these things do. I give a short description, but your best bet is to kind of create a slider and start playing around with those settings. So good luck.